So we are still talking about functions of more than two variables. Somehow from the limits you already saw that the situation actually is not much different from the situation which we have discussed last semester. But since you are not so used to functions of two or more variables, whereas you are more used to a function of one variable from high school, because in high school you have done many examples for limits, you might feel that computing limits of functions of more than one variable is more complicated. Actually, it isn't. It's just a matter of training. So you have to do more examples. If you feel it's more complicated, okay, it's because you haven't done enough examples. The reason why you think for a function of one variable it's easy is because in high school you have done maybe thousands of examples which are all similar. If you do the same for functions of two variables, you won't feel that this is so complicated. But of course, it takes some time to get used to it. And we will see today that also differentiability for functions of more than one variable is kind of looks much more complicated than for functions of one variable. So also this takes some time to get used to it. Okay, but since we have to cover quite a lot of material, we have to move much more quicker than in high school. So you have to do training. You have to, if you feel it's not sufficient just to do the homework assignments, you just have to take your textbook and do some assignments on your own. Okay, so what we want to do today, the goal of the lecture today is to find the notation, a definition of differentiability for a function, first for two variables and then more than two variables. So we look at a function of two variables, and we have last time we have already defined the partial derivatives. Now, one first attempt to define differentiability for such a function. So our goal is to figure out what does it mean that such a function of two variables, is differentiable. If f is a function of one variable, we know what it means. It's differentiable. A certain limit exists, or in other words, the tangent exists. Okay, so this was actually what we have discussed last semester. Now we want to find a similar notation for a function of two variables. And one first easy, maybe the first guess you might have is we define, okay, f is differentiable if those two exist here. Okay, but this is not the way we define it. Okay, because this maybe would be your first thought. Okay, so your first thought would be maybe, okay, we define f to be differentiable if both of them exist. Okay, but this clearly is not enough. If we look at limits, okay, we saw already that if we approach, so if we have a function of two variables, and for instance the function, for instance, is not defined here at the origin. If we just approach along the axis, okay, this does not necessarily mean that the limit exists. This is not enough because you have much more directions. And also this here, these partial derivatives are just certain directions. Okay, so to have a good notation of differentiability, it's certainly not enough just to require that those two exist. Because actually what you want is not to just, you don't want just to look at two special directions. You want, no matter how you approach, okay, you want that f is behaving somehow nice around one point, and this should mean that the function is differentiable. Okay, so the first thing we do is we are going to define the so-called tangent plane, which will be the analog of the tangent line for a function of one variable. So this will be the first step towards definition of differentiability. Okay, now how to define the tangent plane? So okay, we plot let's plot the graph here of this function. So maybe this graph looks like this. Then let's fix a point. Okay, so this, let's say the point with the coordinates x0, y0, and f of x0, y0. Okay, now if we slice this surface here by the plane y is equal to y0, then we get here a cross-section, a trace, which might look like this here, C1. Okay, so C1 is the cross-section by slicing with a plane with the plane y is equal to y0. And similar, C2 is okay, another direction, x is equal to x0. So we have those two cross sections here. So C2 is similar. So this cross section by slicing with the plane x is equal to x0. Now both of them have a tangent, and we know that we can compute the tangent by looking at the partial derivatives. So you have a tangent here, a tangent to C2 at the point P and to C1 at the point P, and the slope of the tangent at the point P is given here by the partial derivatives. This was one interpretation we had of the partial derivatives. Okay, so let's denote by T1 and T2 the tangents to C1 and C2 at the point P. Okay, so you have here two tangents, this tangent and this tangent. And now the tangent plane is defined as the plane which contains T1 and T2 and the point P. Okay, so this is the definition of the tangent plane. So the tangent plane kind of sits on the surface. Okay, so the tangent plane contains T1, T2, and P. Okay, so this is the definition of the tangent plane. Now, computing the tangent plane. So the tangent plane kind of, you can imagine it as sitting on the curve at this point here, P, similar to the tangent. Okay, in case where we have a function of one variable. Now, the computation of the tangent plane, of course, is not very complicated. Maybe let's write this here. Because, okay, whenever you have a plane, we know it should satisfy the equation ax minus x0 plus b y minus. Actually, let's write it already in different form. So let's express it in this form here: a x minus x0 plus b y minus y0. Now, what we have to find is a and b. Okay, but we have the condition that if y is equal to y0, okay, so this means here we slice now the tangent plane with the plane y is equal to y0. What we should get is the tangent T1. Okay, so if we do this, then we get z minus z0 is equal to a x minus x0, and we know that a must be the slope of the tangent T1. So a is the partial derivative of f with respect to x at x0, y0. And similar, you get that p is the partial derivative of f with respect to y at x0, y0. So similarly, p is the partial derivative of f with respect to y at x0, y0. Okay, so you see that an equation of the tangent plane is given by, okay, z is equal to z0. For z0, you can also write f of x0, y0 plus, and then you have the partial derivative of f with respect to x x minus x0 plus the partial derivative of f with respect to y at, times y minus y0. Of course, those evaluated at the point x0, y0. Okay, so you see that in particular, if the function has a tangent plane, okay, the partial derivatives both must exist. Okay, otherwise the function doesn't have a tangent plane. So this you have to require. Okay, so if the function, if the partial derivative of the function both exists at the point, then you can define the tangent plane like this here. Okay, otherwise the tangent plane does not exist. Okay, so the tangent plane sometimes is also called the linear approximation. So we will normally denote here also this function here. So this function f of xy plus the partial derivative of f with respect to x minus x0. Sorry, this should be x0 or y0 plus the partial derivative of f with respect to y. Y minus y0. So this function will be called normally the linearization of f at x0, y0. And we will normally write that because the tangent plane somehow should approximate the function. Okay, so we will normally write we will sometimes write something like this here. So you can use the tangent plane in order to approximate the function, and this is called the linear approximation of f. Of course, at the point x0, y0. Okay. If we think back last semester, why did we consider the tangent? Because the tangent was an easy way to approximate the function, or gave an easy function which helped us to approximate the function locally around the point. And similar here. So you have the tangent plane at some point x0, y0, okay, and this the tangent plane normally in many cases will give you a not so bad approximation of the function locally at x0, y0. Okay, so this is the tangent plane. Okay, so for the existence of the tangent plane, the only thing you need is that the partial derivative both exist. If you read the corresponding chapter in our textbook, the author assumes that the derivatives must be continuous as well. I found this very, very confusing when I read this for the first time. Actually, it's not necessary, because for the tangent plane, the only thing you need that the tangent plane exists is, as we have seen here, because this is the equation here of the tangent plane, the only thing you need is that the partial derivatives exist. Whenever the partial derivative exists, you have something like the tangent plane. Okay, but the next question we should ask ourselves is, okay, how good is this approximation? So is existence of the tangent plane, like when the partial derivative exists, okay, you have a tangent plane. Is this already enough to ensure that the tangent plane is a good approximation of the function or not? This is the next question which we should ask ourselves. Because from a differentiable function f, okay, if we reconsider the definition of last semester, okay, what we expect is not only that the tangent line exists, okay, this is not the only important thing. The important thing is that the tangent line really approximates the function locally, okay, and that this approximation is good in some sense. So how about here? Okay, is the tangent plane always a good approximation of the function? Okay, if it's always a good approximation of the function, we would say, okay, a function is differentiable if the partial derivatives both exist, and this would be enough, because then we have a tangent plane, and the tangent plane approximates the function very well. Okay, so let's look at an example. You find in our textbook this example, I think it's 2x squared plus y squared. So let's stick to the same example. This is a very easy function. So this is an elliptic paraboloid. The surface is an elliptic paraboloid. The point we consider is 1, 1, 3. So of course it's easy to come up with the tangent plane or linearization or linear approximation. Everything is the same. Okay, so okay, we have to evaluate the function at the point 1, 1, which is 3 plus. Then we have the partial derivative with respect to x, which is 4. 4x evaluated at 1, which is 1. So we have 4 here times then x minus 1 plus. And then the partial derivative with respect to y, which is 2y evaluated at the point, which is 2. And then x minus, y minus 1. Okay, so this is the tangent line. This is the linearization in this case. Plus 2y minus 4 minus 6 minus 3. Now, I didn't bring Maple today, so you have to look in your textbook. There is, let me check it, figure 2 on page 924. So if you use Maple now, okay, and you plot this function, you plot the graph of this function, and you plot the tangent plane, okay, if you move into the point 1, 1, okay, if you make your filling rectangle smaller and smaller, so you move into this point, okay, you will see that the function, the graph of the function, you see this in our textbook. There are 3 plots, okay, where you always see this function here together with the tangent plane, okay, and as you move in, as x and y are getting both closer to 1, 1, okay, you see that the tangent plane behaves more and more like the function, okay? Or in other words, if you plot this function, okay, over a very small filling rectangle, okay, around 1, 1, okay, then as you make your filling rectangle smaller and smaller, the function looks more and more like a plane, okay? So in this case, you would say, okay, the tangent plane is a very good approximation. It's a good approximation of the original function. Okay, so here we see an example where the tangent plane approximates the function quite well. Okay, but here is another example where we see this is not always the case. So existence of the tangent plane is not enough to ensure that the tangent plane, that the linearization or the linear approximation is a good approximation. Now, this example we already discussed before. So we have x times y over x squared plus y squared if xy is not equal to 0, 0, and 0 if xy is equal to 0, 0. Okay, so what is the tangent plane of this function at the point 0, 0, 0? Okay, so the tangent plane at the point at 0, 0. Okay, so for this we have to compute the partial derivatives. So the partial derivative of f with respect to x. Actually, if you don't have to really to take the derivative here, okay? Because the partial derivative with respect to x means you keep y constant. Y is equal to 0. Okay, so you look at y is equal to 0. Here in this case, for y is equal to 0, what do you get? 0, and here 0. So the function which I called c1, okay, is identical 0. So the tangent equal to 0. Okay, so this is 0. Okay, you should this kind of the computation how I compute this. Okay, it's kind of trivial, but you should realize that you do not have to first to take the derivative here and so on and so forth. Okay, you don't have to do this. Okay, then or you don't have to look at the limit. Not at all. Okay, you have to. The only thing you have to do is because you know that this is actually I should write this more clearly because this is at the point xy is equal to 0, 0. But since I only care about the change in x direction, okay, I can first already plug in y is equal to 0. So I plug this in. I look at the corresponding function. What is the function if y is equal to 0? Okay, you see the function is identical 0, so the slope of the tangent must be equal to 0. So this is 0, and the partial derivative of f with respect to y at xy is equal to 0, 0. You use the same reasoning, equal to 0. You shouldn't be confused here because we know that this function, okay, is not continuous at 0, 0. But still the partial derivatives both exist. Okay, it is not the case that if the partial derivative both exist, then the function must be continuous. This is not the case. Okay, so this is important. This is an important remark. So you should realize that this function is not continuous at 0, 0. It does not mean that the partial derivatives do not exist. Now, so what is the tangent plane, or what is the linear approximation? You see, okay, 0, identical 0. Okay, because the function value at 0, 0 is 0 plus this is 0, so I can forget about x minus 0 plus this is 0 times y minus 0. So it's the tangent plane is identical 0 at the point 0. Okay, but this is not a good approximation of the function. Why? Because you see, this is very easy to see, because you see that that f of x, okay, as long as x is not equal to 0, okay, if you plug this in, you see it's always 1/2. Okay, so as your x is moving close to 0, so you have here, if I just plot the xy plane, if I approach 0, 0, if I approach 0, 0 along this line here, I'm always standing at 1/2. Okay, but the tangent plane at the point 0, 0 is exactly what you see here, the xy plane. Okay, so the xy plane only in the point 0 is a good approximation, but if you leave a little bit 0, 0, the approximation is not very good. So you see that those two examples are quite different. In both examples, the tangent plane exists. Okay, so here you have the tangent plane, which is 0. Here you have this tangent plane. Okay, so existence is not a problem of the tangent plane, but the behavior, the approximation behavior of the tangent plane is very different in those two examples. Here, as you move into the point 1, 1, this function will look more and more like a plane. But here, as you move into the point 0, 0, this function will not look more and more like a plane because of this here. Because here you have always 1/2. Okay, but if you approach here, okay, always 0. So this function locally does not look like a plane. Okay, and now I can tell you what is the definition of differentiable for a function of two variables. We will define a function. We will call a function to be differentiable if the tangent plane approximation or linear approximation is a good approximation. So in this case, we will say the function is not differentiable at 0, 0, whereas in this case, the function will be differentiable, will be called differentiable at 0, 0. Now, this is not very precise. What do I mean by the tangent? In which sense should the tangent plane be a good approximation? I have to make this precise. But the definition, okay, which you will see in a minute, just says this, that the tangent plane, that the function is differentiable if the tangent plane is a good approximation. This is a little bit different. You shouldn't be too confused here because it's different from last semester. Last semester, if the tangent line exists, okay, this is equivalent to the function is differentiable. Okay, this was our definition of differentiability of a function of one variable was the tangent line must exist. Okay, so, this is not very precise because actually we first defined differentiability and then we defined the tangent line. Okay, but it's more or less equivalent. Here, existence of the tangent plane and differentiability is not equivalent. Okay, you have to say so. Differentiability is more than just existence of the tangent plane. Okay, so now. If we recall what we have done last semester, okay, so differentiability last semester. So if we have a function of one variable, okay, so this is the situation we understand very well. So what we look at is delta y is equal to f of x plus delta x minus f of x. Now, one way to define differentiability, or we saw last semester that f is differentiable if and only if. Assume already that f is differentiable. Okay, then we know that I showed you last semester, and maybe you don't remember this property because it didn't look very important last semester. But I told you last semester this is a very important property, and I will talk about this next semester in more details. So if you have a differentiable function, then you have this here. So that this is the difference between the function values is equal to this is what we call the differential, okay? Plus, and then you have here an epsilon times delta x, okay, where epsilon tends to 0 as delta x tends to 0. Who remembers this? I needed this in order to prove the chain rule last semester. Okay, so maybe you could, if you find this where you find the proof of the chain rule. Okay, I needed this for proving the chain rule. Okay, I wrote if f is differentiable, I wrote it like this here. Now you see what does this mean here? So here you have the difference between the function values. So you change x by delta x, and you see here the difference between the function values. This is the same difference, but if you look at the tangent instead of the function, and here you see, okay, what is the difference between? The difference is getting small as delta x is getting 0. So this means that if you rewrite this, because you can write this as f of x plus delta x is equal to, and then you get here the tangent. Okay. So this means more or less that whenever f is differentiable, you have a function of one variable, f is differentiable, then this means that the tangent is a good approximation in this sense here of the function. Okay, so this tells you something like the tangent, if for a differentiable function, the tangent is a good approximation. Okay, now this is what we are going to use in order to define differentiability of a function of two variables. So we will just model this kind of behavior. Okay, so what is the definition? So kind of this is our starting point. Okay, so f is called, so we have a function of two variables. F is called differentiable. If, okay, now just similar, okay? So we look here at delta z. So delta z is also maybe I should write this as f of x plus delta x y plus delta y minus f of x y. Okay, and this should be close to the approximation you get from the tangent plane. So we write this, okay, is equal to partial derivative of f with respect to x times delta x plus the partial derivative of f with respect to y times delta y plus, and then we have an error. Error is epsilon 1 delta x delta y delta x plus epsilon 2 delta x delta y delta y. And we require that both of those functions tend to 0 as delta x delta y tends to 0 0. Okay, so this is what differentiability means. This is the definition of differentiability. And what does it mean? You see, what you have here, okay, is if you because f of xy plus this chunk here, okay, is the tangent plane. So you have here the difference between the function value and the tangent plane, and the difference should get small, okay, as the point delta x delta y is moving to 0 0. So this just tells you that the tangent plane should approximate the function well. So for a differentiable function, the tangent plane will approximate the function well. Okay, so any questions to this? Now, of course, the first question which we have is, okay, how should I apply this? Okay, if I have given a function, okay, how should I check now that the function is differentiable? Of course, one possibility would be, okay, you just check the definition here. So you have to find the epsilon 1, epsilon 2, and you have to write this difference in this form. It's possible. It's not too complicated, okay, but possible for some functions, but wouldn't be very convenient. Okay, so the first question we are interested in is, okay, so obviously, what you need that the function is differentiable. What you certainly need is partial derivatives exist, okay? Because if the partial derivatives do not exist, you do not even have a tangent plane, okay? So then you cannot talk about differentiability. So you certainly need, for a function to be differentiable, you need that both partial derivatives exist, okay? But this is not equivalent, okay? So maybe I write this on the blackboard. Such questions occur very often in the Heu-Kau. So like multiple choice, and one of the choices is something like this here. F is differentiable. Okay, yes, this is true. Okay, so if f is differentiable, both partial derivatives must exist. Then sometimes you have in the Heu-Kau the question, if both partial derivatives exist, is f differentiable? Okay, no, it's not true. Okay, so this is not true in general. We saw already an example. Okay, so the example which we saw was this example xy over x squared plus y squared. If xy is not equal to 0, 0, and 0, if xy is equal to 0, 0. But of course, it would be interesting to know. Okay, so is it possible to add something? So maybe you add something to this requirement. Okay, and then you really get that. So you add one condition, and those two conditions maybe imply differentiability. And there is really such a theorem. So the only thing you have to add is continuous. If the partial derivatives exist close to a point AB, and both are continuous at AB, then the function is differentiable. So this gives you a quite convenient result to check whether a given function is differentiable or not. So if the partial derivatives exist for xy close to AB, this is something which we in mathematics called in the neighborhood of AB. So not only in AB, but a little bit, you find something like, you can think about it, a little circle around AB where the partial derivatives still exist and are continuous. At AB, then we have that f is differentiable at AB. Okay, so this is very convenient. So this tells you that here the inverse almost true. Okay, the only requirement you have to add is that the partial derivatives are continuous at the point. Okay, so this is the inverse here almost true. Okay, the only thing which you have to add is continuity of these two functions at the point AB. Okay, and continuous here is not just in one direction. Okay, it's a function of two variables. Now, do you find that the proof in our textbook? Do you want to see it? Or the proof is actually quite easy of this result here. Not very complicated. And as always, the proof is using not a surprise, using the mean value theorem, as always. Okay, so maybe, because the proof is so easy, so maybe let's discuss it. Just to see, because this is the only, you don't have to be afraid that you have to check this kind of assumption, okay? For the next assignment, I have one example where you have to check this directly. You should directly use this definition. Okay, so you only have to do it once, okay, to see that it works, okay? But you don't have to be afraid, because afterwards you don't have to use this anymore. Okay, you can use this here in order to check that the function is differentiable, because most of the functions will satisfy these conditions here. Okay, of course there are some exceptions. Now to see once how to verify this maybe not so easy looking definition, maybe let's prove this here. So we have to look at this here, f of x plus actually a, because a is the point we are interested in. A plus delta x, b plus delta y minus f of ab. Now the trick is to rewrite this in the following form. So you write this as, so you add something. This, if you have done a little bit proving in mathematics, these kind of tricks are quite standard, are quite easy. So the trick is to add something like this here, and then to subtract it, and then to add it again, and then minus. Okay. So I haven't done anything now. Okay, but what I have gained is the following. Okay, if you look at something like this here, for something like this, I can apply the mean value theorem. Okay, this is what I have gained. Okay, but because you see that here we can use the mean value theorem, because now the second coordinate is fixed. Okay, and with respect to the first coordinate, we have that the function f is continuous. Okay, because it's even differentiable with respect to the first coordinate. So here, if I fix the second one, okay, then I essentially look at the problem boils down to a problem of a function of one variable. And this here tells you that the derivative exists, so the function must be continuous also. Not the function as a function of two variables, but as a function of the first coordinate. Okay, so you see that this function here, if you fix this, satisfies the requirement of the mean value theorem. Okay, so you can apply the mean value theorem here. So what you get is, okay, so you take the derivative with respect to the first coordinate, and then you have some point, call it c, which is between a and a plus delta x. And this one is fixed anyway, times delta x. This is what you get from the mean value theorem. And here the same. But here is the first coordinate is fixed, the second is changing. Okay? But again, because we assume also that the partial derivative with respect to y exists, I haven't used yet, you should observe, I haven't used yet this condition. Okay? So this I can do even if the function is not continuous at the point ab. I don't need this requirement at the moment. So you see here the partial derivative of f with respect to y, and then you have a, and here I have a d which is sandwiched between b and b plus delta y and delta y. Now this already looks quite like this is already quite in the form of the definition of differentiability, because I have already that the difference is equal to, here I almost have the partial derivative delta x plus the partial derivative delta y, almost. Okay. So what I do is, okay, because actually what I want to have, if you look at the definition, that what I want to have is the partial derivative with respect to x, actually not at c and b plus delta y, but I want to have it at ab delta x plus, and here the partial derivative of f with respect to y, ab delta y. Okay, but this is not really correct. So I have to subtract both of them, and then I have to add those. And now I merge. So I merge certain functions to one. So I will tell you in a minute what epsilon 1 is and epsilon 2. So what is epsilon 1? Epsilon 1 is so this is with respect to delta x. So I have this guy here. So the partial derivative of f with respect to x, c b plus delta y, and then I have to subtract this one because this one I added. So the partial derivative of f with respect to x ab. And I have the other one is this one. What ad minus y. Right, so the only idea which I used is the mean value theorem here. The rest is just rewriting. And now, as delta, so if delta x and delta y tends to 0, 0, what happens with this point here? So C is where? C is between A and A plus delta x. If delta x is going to 0, okay, C is moving to A. Okay, and this point is moving to B. So this point is moving to AB. Okay, but I assume that this function is continuous. So this means that this difference must go to 0. And the same here. Okay, finished. Because I have to find, this is what I have to prove, because I have to show that I can write the difference as the linear this is not really the linear approximation. I can write the difference as this part here, plus I can add something which is getting small as delta x and delta y tends to 0, 0. Okay, and this I have done. Okay, so you see, very easy to prove, not complicated. Only the mean value theorem. It's always the mean value theorem. So we more or less, since we learned the mean value theorem, this is the only idea we used, more or less. Okay, it's the mean value theorem. So all our results, everything we can do is based on the mean value theorem. Now, just to show you a very easy example that you understand. I just choose the same example as you find in the textbook. So you have this function here. Okay. Let's look at the points AB is equal to 1, 0. Now, the first question is, okay, why is this function here differentiable? So is the function differentiable at this point here? And now, because you might say, okay, it looks differentiable, okay, because I know these kind of functions and it looks differentiable. But this is a function of two variables, and our notation of differentiable is slightly different, okay, than the notation we have seen in last semester. Okay, so you shouldn't argue. You shouldn't say like, okay, it looks differentiable. Of course, this function is differentiable. This is the reason why you say this is because you have seen it for functions of one variable. Okay, but still, this is new here now because it's a function of two variables. So how do we argue that this function is differentiable at this point? Okay, so what we do is we compute the partial derivatives. Okay, we see that the partial derivatives for this function, because this function is differentiable everywhere. Okay, as a function of the partial derivatives exist everywhere. Okay, so you see with respect to x is e to the xy plus xy e to the xy, and then the partial derivative of f with respect to y is equal to x squared e to the xy. And you see that both of them are continuous, okay, also everywhere. So they are continuous, but as functions of two variables, not as function of one variable, okay? Maybe for a function of two variables, why do we know that this function is continuous? Don't say because it looks continuous, okay? Because then you just use what you have seen already in high school, okay? But because for continuous functions of two variables, okay, we have a similar building procedure like for functions of one variable. So we know that this is continuous, we know that this is continuous, we know the product is continuous, and so on and so forth. We know that e to the is continuous, and if you do composite functions, continuous, and so on and so forth. Okay, so that's why this function is continuous as a function of two variables, and this function is also continuous as a function of two variables, which means that this function is, because of this theorem, differentiable at every point, in particular this point here. So, and both are continuous. So we can use our theorem. F is differentiable. So this means if you compute the tangent line approximation, so the linear approximation of this function is easy to compute. So you first evaluate this function at 1, 0. Then what you get is 1 plus. And then you have the partial derivative of f with respect to x at 1, 0. So this is 1 here. 1 times x minus 1 plus. And the partial derivative of f with respect to y at 1, 0 is also 1 times y. Okay, so what you have is 1 plus, this is minus 1, so what you have is just x plus y. And because this function is continuous, okay, at this point here, sorry, it's differentiable at this point, this means that if you are very close to 1 and 0, okay, you can use this simple function in order to approximate the function value of this function. Okay, this is because we know that the function is differentiable. Okay, so this theorem, you can use this theorem in order to check whether a function is differentiable. Okay, so what you have to check is that the partial derivatives exist and are continuous. Okay, if these assumptions are satisfied, then you can conclude that the function is differentiable. Now, of course, the question is, okay, how about this function are not satisfied? How about these assumptions are not satisfied? Indeed, there are functions which are differentiable, okay, but do not satisfy these assumptions here. Okay, so because this is just if these assumptions are satisfied, you can conclude this, okay, but not the other way around. Okay, so if these assumptions are not satisfied, of course, if the partial derivatives do not exist, okay, there is no way the function is differentiable. But if the partial derivatives exist, the function is not, and the partial derivatives are not continuous, okay, then you still might have that the function is differentiable or not differentiable. Okay, so we saw already one example where the partial derivatives exist. We didn't check whether the partial derivatives are continuous or not. So we saw already this example here. Here the partial derivatives, we saw that the partial derivatives exist. Actually at the point 0, 0. Sorry. At the point 0, 0. Okay, we saw that the both partial derivatives exist here for this function. Okay. I gave you already kind of heuristic reason why this function is not continuous. It's not differentiable at 0, 0. Okay, but actually, if we really wanna, how do we show that this function is not differentiable at 0, 0? Okay. Now, of course, because we know already that this function, or we have already guessed that this function is not differentiable at 0, 0. So no way that the partial derivatives are continuous. Okay, at least one of them must be discontinuous. Okay, but still, how to argue? Okay, one way you could argue is, okay, you look at the definition of differentiability and you show that you are not able to find two functions epsilon1 and epsilon2 such that you can write delta z as partial derivative of f with respect to x times delta x plus partial derivative of f with respect to y times delta y plus some epsilon1 delta x plus epsilon2 delta y. So you have to show that such two functions, epsilon1 and epsilon2, do not exist. Okay, you cannot find such functions. And this actually is one of the homework assignments. Use the definition of. So this is just once. Okay, I admit this is not a very easy example, but at least once you should try to understand that how to use the definition to prove that this function is not differentiable. But actually, there is a more easier way. Okay, because for this function to argue. Because we know already this function is not continuous. So from this you might think, okay, this should actually this should actually imply that the function is not differentiable. So we should have something like, if a function is differentiable, then the function must be continuous. So let's prove this first. So if f is differentiable, at AB, then f is differentiable. Then f is continuous. You shouldn't be confused here. This always means differentiable and continuous always as a function of two variables. Okay. So if f is differentiable at AB, then f is continuous at AB. This, of course, is easy to prove. This is actually an exercise in our textbook, but it's so easy that I show it to you. So it's because what does it mean? F is differentiable. What does it mean? This means that there exists a function epsilon 1 and epsilon 2 such that you can write the difference write the difference as okay, the partial derivative of f with respect to x, x minus delta x, plus the partial derivative of f with respect to y, delta y, plus, and then you have this function epsilon 1 delta x plus epsilon 2 delta y. And now, okay, this is differentiability. Differentiability means this here. Okay. Now, as delta x and delta y tend to 0, 0, this here tends to 0, this tends to 0, this tends to 0, this tends to 0, and those two functions by definition tend to 0. So everything tends to 0 as delta x, delta y tends to 0, 0. This is more or less the definition. Okay, so this tends to 0. Of course, this tends to 0. This is a constant. This tends to 0. This is a constant. This tends to 0. This is not a constant. Okay, this epsilon 1 is a function of delta x and delta y, but by definition tends to 0. This tends to 0. This tends to 0. This tends to 0. Okay, everything tends to 0. So you see that as delta x, delta y tends to 0, 0, this function tends to f of AB, continuous. Okay, so f is continuous at AB. And this will allow us easily to argue, okay, that this function is not differentiable. So why is this function not differentiable? Because this function is not differentiable at 0, 0. Okay, so any questions to this? So more or less, these are the two cases. So if you have a function which is differentiable, most of the time you just check that the partial derivatives exist and are continuous. If you have a function which is which you suspect to be not differentiable, most of the time the function is not even continuous. But there are functions which are where the partial derivatives exist and the function is continuous. Okay, but still it's not differentiable. And for this case, okay, it's not so easy to check because you have to really go back to the definition and use the definition to check it or do something similar. Okay, but fortunately, these functions look exotic. They are more. Those are not the functions we normally encounter very often. So I won't give you an example. Sometimes they occur in some as a more complicated example in the Hoi-Kao. I remember there was once the function which was this. So it's but it's, as I said, this function, such functions, you can try to construct one. It's not very easy. So a function where the partial derivatives exist, so like this one, but in addition the function is also continuous but not differentiable. It's not so easy to construct such a function. I'm not sure. I don't think that the textbook has one example. Maybe there is one. I don't remember. The examples are normally of the form somehow like x squared plus y squared times the sine of 1 over x squared plus y squared, or something like this. But I would have to think also for 10 minutes to figure out an example. Okay, so any questions to this? You see that the situation for functions of two variables is quite different. Okay, I told you already, you find this in our textbook in section 14.4, but I think the explanation there are very confusing. Okay, because the author assumes from the beginning that the partial derivatives are already continuous. Okay, so there doesn't seem to be any problem. Okay, for a function to be differentiable, because if you have partial derivatives and they are continuous, then the function is automatically differentiable. So it might be a little bit confusing if you read this in our textbook. But actually, this is not so complicated. It just takes some time to get used to it. If you see it, and I'm sure you see it for the first time, maybe you will find this is pretty complicated and pretty different. Okay, but actually, if you think a little bit about it, it's quite natural how things are defined here. Okay, so any questions? Now, another topic which is discussed in our textbook is differentials. And this is pretty similar. This is not even completely similar to what we have done already last semester. So you remember last semester we defined if you have a function of one variable, then normally you can use this notation to denote the derivative of the function. But we also defined here this guy and this guy. Okay, but in a different sense. Okay. Somehow related to this definition here, but a little bit different. Okay, so this of course is still one symbol. Okay, so we had a different definition for dx and dy, not really connected to this symbol here. Okay, but somehow we were looking at this situation and defining them. So how did we define them? Now dx was for us an independent variable. Okay, and dy was defined as the derivative of f of x. I shouldn't write it like this because then it looks like how to write this that you're not confused. So dx is an independent variable. And then dy is equal to the derivative of f of x dx. You shouldn't be confused by this. This is a definition here. Okay, this doesn't mean. Of course, you can say, of course, this is clear because I see it here and I multiply everything with dx. But because this is one symbol here. Okay, and you cannot multiply with dx. So the way we define dx is an independent variable. You can, for instance, you can set dx equal to 2. Okay, so it's a variable, and then you define dy as a dependent variable in this sense here. Okay, and the interpretation of this dy is pretty clear. Just all this. So if this is our function, and we have at some point, so this is x here, and this is x plus delta x. Okay, and delta x is equal to dx, because or I should maybe because dx is an independent variable. So for instance, I can choose it equal to delta x. Then if I plot the tangent here and I plot this line here, then here you see dy, and from here to here you see delta y. Okay, so this dy will approximate our delta y. Okay, so that's the reason why we considered differentials. So this is just maybe a complicated way to write that you can use the tangent line in order to approximate the because this is the approximation you would get the difference of the function value which you would get if you would replace the function by the tangent. And it's kind of, this tells you, it's a complicated way of saying that the tangent line approximates the function. Okay, now we want to do the same for functions of two variables, so we just use the same idea. So how do we do things for functions of two variables? More or less, this is just notation, okay, but notation which you might encounter in applications. So now you have a function of two variables. Okay, so now we say dx and dy, okay, are independent variables. And we define dz. So this is a definition here. We define it as the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Okay, so those two here are independent variables, and this is here dependent. Okay, and you have a similar picture. Now, wait, I have to, because I'm not good in plotting such things. You have this picture in your textbook, but I still try to make a plot on the blackboard. Okay. No. Okay, so this is x here, this is y, this is z. Now this is the graph of our function. And this is the point which we consider. Okay, and and this what you see here is the tangent plane. So this is the tangent plane at this point here. Okay, now if this here, so this is our point. This is the point xy which we consider. And now we assume that this length is delta x, and this are equal to dx, and this length is delta y or equal to dy. Okay. Then what you see here, because this is the function value, okay. So you see here, you see dz, and now this is not very good because and here you see delta z. Okay, so delta z is the change. Delta z is a change in the function value. Okay, if you replace x by x plus delta x and y by y plus delta y, then this is the change in the function value delta z. And the dz is the corresponding change if you replace the function by the tangent plane. Okay, so we again have that dz is equal to delta z. Okay, so all this is kind of like complicated way of writing because this just expresses that the tangent plane is a good approximation, approximates the original function. Of course, you need differentiability. That's this is here is a good approximation, but this is just notation for writing that the tangent plane is an approximation of the function, and this is sometimes used in applications. In particular, if you measure something and there is an error involved, and you want to understand, and you have an absolute error, and you want to try to understand, okay, what is the effect of the if you have certain quantities and you want to use those quantities to compute another one, so you have a relation between quantities, and every quantity you measure it with an error, and you want to know what is the effect on the quantity you want to compute, then normally you argue with differentials. I show you one example. But this actually is easy stuff, just complicated notation. Or not so complicated notation. So you have to digest this once, and then it's quite easy. For instance, we have a circular cone. Okay, we all know that the volume of the circular cone is Okay, and what we do is we measure the radius of the base and we measure the height of the cone. Okay. Okay, so let's assume that for the radius we have 10 centimeter plus minus. So, and we have an error in measuring the radius. So the error is, absolute error is plus minus 0.1. And for the height, the same. So you have 25 centimeter plus minus 0.1 centimeter. And what you want to understand is, okay, what is the error induced? If you use this and this here in order to compute the volume, okay, what is the error induced for the volume? And what you do very often in applications is you do an approximation, because normally the relation will be very complicated, and if it is a very complicated function, you replace it by the tangent plane. If it is a function of two variables, and use the tangent plane in order to approximate the error instead of using the original function. Of course, if things are so easy here, you could do it much more precisely. But you will see that looking at the so actually what you have is what you want to have is the delta, the absolute error in v, but you can approximate this by dv. Now dv is okay by the definition. The partial derivative, okay, the partial derivative of v with respect to r, so this is 2 times pi times r h over 3 times, and then you have delta r plus, and then the partial derivative with respect to h, so p times r squared over 3, and then delta h. Okay, and this is kind of easier because it's a linear function, so if you want to understand the absolute error, so you just take the absolute value here. So what you get is 2 times pi times r times h over 3, and r and h are those two here, times delta r. So actually here I should write here d, sorry, but for dr I can choose delta r, and for dh I can choose delta h. Then I have here plus pi r squared over 3, and then here I have the absolute value of delta h. And then you plug everything in. So delta r is 0.1, delta h is 0.1. R and h are those two quantities, and you get that this is equal to something. 36 cubic centimeter. Okay, so this is the easy principle behind it, but that's the way we look at, that's the reason why we look at differentials. But actually, this here is just a maybe more complicated way of writing that this what you look at this involves the tangent plane, and this involves the original function, and you just replace the original function by a tangent plane, and you use the difference if you replace the original function by a tangent plane to approximate the original the difference in the function values. Okay, now I still have some time left. So now, of course, you can do everything for functions of. If you like this kind of stuff for functions of 2 variables, you can define it for functions of 3 variables. For functions of 3 variables, we have a similar notation for the linear approximation. We have a similar notation for differentiability. I think differentiability is not even defined in our textbook, but you also have a similar notation of differentials. So maybe let me write this down very quickly. So if you have a function of 3 variables and you have a point which is now a, b, c, and so let's not choose a point on the surface, but let's just choose a point. Then again we can define the linearization, which is which will for differentiable functions will approximate the original function, and here what we have is f of a, b, c plus the partial derivative of f with respect to x minus a plus the partial derivative of f with respect to y minus a plus the partial derivative plus the partial derivative of f with respect to z minus c. Okay, and this will be called the linearization or linear approximation at a, b, c of the original function. Now, the function will be called differentiable if the linear approximation is a good approximation in a certain sense, in a similar sense as for functions of two variables. And again, we say normally that, but this is just a tiny variation. We say that dx, dy, and dz are independent variables. And then we define dz as, and this is the definition, as the dependent variable, which is the partial derivative of f with respect to x dx, plus the partial derivative of f with respect to y dy, plus the partial derivative of f with respect to z dz. And again, we have but actually this just means the same as this here, just in a different language. So this should not be confusing for you, okay? Because this is just, it's more or less the same, okay? You just here introduce some new notation and you rewrite this slightly different as this here. Okay, so next time we will generalize the chain rule to functions of two and more variables. This is essentially what we want to do next time, and then then it's time to discuss applications of the theory of functions of two variables. So then we are going to discuss things like, okay, given a function of two or more variables, okay, how to find like extreme values of this function, how to find local extrema, how to find global absolute extrema, and similar questions. So this is more or less similar things as discussed last semester, but now for functions of two and more variables.